In this lesson, we will talk about approximate methods used in quantum mechanics. Paul Dirac famously noted in 1929 that the fundamental laws governing physics and chemistry are already known. The challenge is not the laws themselves, but rather that, when we try to apply them exactly, the resulting equations become far too complicated to solve. This is especially true for the Schrödinger equation. While we can obtain exact solutions for simple systems like hydrogenic atoms, such solutions are generally not available for more complex systems. The difficulty arises because analytical solutions quickly become mathematically intractable, and even numerical solutions can require significant computational resources, particularly for many particle systems. As a result, the practical approach in quantum mechanics is to rely on approximate methods. In this lesson, we will focus on two of the most important approaches, the variational theorem and perturbation theory. Let's take a look at the variation theorem. The theorem states that if we choose a trial wave function phi that satisfies the same boundary conditions as the true wave function psi, then the expectation value of the Hamiltonian with respect to that trial function, denoted here as W, will always be greater than or equal to the true ground state energy, E sub 1. We will refer to W as the variational energy. In other words, any reasonable guess for the wave function provides an upper bound on the ground state energy. To understand why this works, recall that the exact wave functions form a complete set. This allows us to expand our trial function as a linear combination of the exact eigenfunctions, with coefficients C sub 1, C sub 2, and so on, ordered by increasing energy. Since the Hamiltonian is Hermitian, we can choose an orthonormal set of eigenfunctions for our complete set. It's easy to show that the numerator in the expression for W is just a weighted sum of the energy eigenvalues, with weights equal to the squared magnitudes of the coefficients. Now consider the denominator. This integral is simply the sum of those same weights. As a result, the variational energy W can be interpreted as a weighted average of the energies of all the eigenfunctions. Since E sub 1 is the lowest possible energy, any weighted average that includes higher energy terms must produce a value of W that is greater than E sub 1. Note that the denominator is equal to 1 if phi is normalized. Therefore, if you encounter an expression for W without the denominator, it should be understood that this normalization condition has been assumed. The variation theorem is extremely useful because it tells us that, by improving our trial function, we can systematically approach the true ground state energy from above. Let's now look at an example. Consider the trial function phi equal to x times L minus x for a one-dimensional particle in a box. First, we verify that this function obeys the same boundary conditions as the one-dimensional particle in a box wave functions. When x equals 0, phi becomes 0 times L minus 0, which equals 0. When x equals L, phi becomes L times L minus L, which also equals 0. So this trial function satisfies the required boundary conditions. Now, we proceed to verify that the expectation value of the Hamiltonian with respect to phi is greater than or equal to the ground state energy, E sub 1. A good resource to evaluate definite integrals is Wolfram Alpha. From the Wolfram Alpha website, we can easily find that the numerator is equal to h bar squared over 2m times L cubed over 3. If we evaluate the denominator, we find that it is equal to L to the 5th power over 30. Plugging the definite integrals we just evaluated into the expression for variational energy W, we find W to be equal to 10 times h bar squared over 2ml squared. You can easily verify that this is greater than the true ground state for a particle in a box of length L, which we can write as pi squared times h bar squared over 2ml squared. The relative error is 1.32%. Here's a comparison of the normalized trial function phi in blue and the exact wave function in purple from x equals 0 to L. Note that for comparison, the trial function needs to be normalized. This can be done by multiplying it by square root of 30 over L to the 5th. We can take advantage of the variation theorem to develop a systematic and practical approach for finding the best possible approximation to the ground state energy. Such an approach is known as the variational method. One common strategy is to use a trial function that contains adjustable parameters. For example, if we introduce parameters a, b, c, and so on into the expression for the trial function, then the variational energy W becomes a function of these parameters. Our goal is then to determine the values of the parameters that minimize W. To do this, we set the partial derivatives of W with respect to each parameter equal to 0. That is, we solve equations such as partial W with respect to A equals 0, partial W with respect to B equals 0, and so forth. This procedure allows us to obtain the best possible approximation to the ground state energy within the chosen form of the trial function. Now we introduce the linear variational method. In this approach, we use a trial function that is written as a linear combination of a set of functions. So, our trial function phi is expressed as c sub 1 times function f sub 1 plus c sub 2 times function f sub 2, and so on. The set of functions f sub 1, f sub 2, and so on is called the basis set, and the individual functions in the set are called basis functions. The variational energy, W, then becomes a function of the coefficients c sub 1, c sub 2, and so on. Our goal is to find the values of the coefficients that minimize W. To do this, we solve a set of simultaneous equations by setting the partial derivatives of W with respect to each coefficient equal to 0. The linear variational method is especially useful because the coefficients can be determined and computed efficiently using numerical methods. When we minimize the variational energy with respect to the coefficients, we obtain a system of simultaneous equations. If we use n basis functions, then we need to solve n simultaneous equations, known as secular equations, with n plus 1 unknowns. For example, if we use two basis functions, we need to solve equations 1 and 2 as shown here. The unknowns are the coefficients c sub 1, c sub 2, and the variational energy W. In these equations, the coefficients are multiplied by expressions that involve integrals denoted here by h sub ij and s sub ij, for I equals 1 to n and g equals 1 to n. The integral h sub ij is represented by this Dirac bracket notation, where the Hamiltonian operates on function f sub j, then multiplied by the complex conjugate of function f sub I, and then integrated over all space. The integral s sub ij is represented by this Dirac bracket notation, where the function f sub j is multiplied by the complex conjugate of function f sub I, and then integrated over all space. The secular equations are such that, in equation I, the sum over each coefficient c sub j is multiplied by h sub I j minus ws sub I j is equal to 0. For example, in equation 1, coefficient c sub 1 is multiplied by h11 minus ws11, and coefficient c sub 2 is multiplied by h12 minus ws12, and their sum is 0. The system of simultaneous equations can be written compactly in matrix form as A times C equals 0. For n basis functions, the matrix A is an n by n matrix, often referred to as the secular matrix. Each element of this matrix, A sub I j equals H sub I j minus Ws sub I j. For example, if n equals 2, the secular matrix takes the form shown here, with elements H11 minus Ws11, H12 minus Ws12, and so on. The coefficients form a column vector with n elements, called the eigenvector. For n equals 2, this vector consists of C sub 1 and C sub 2. Putting everything together, the matrix equation becomes secular matrix times coefficient vector is equal to the 0 vector. Note that the dot product of row 1 of the secular matrix with the eigenvector is equal to 0. This is equivalent to what we previously wrote as equation 1. Similarly, the dot product of row 2 of the secular matrix with the eigenvector is also equal to 0, which corresponds to what we previously wrote as equation 2. Now, let's examine the solutions to the secular equations. First, there's a trivial solution, where all coefficients are equal to 0. However, this solution is not physically meaningful. What we are interested in are non-trivial solutions. These exist only when the determinant of the secular matrix is equal to 0. So we set the determinant of A with elements h sub I, j minus ws sub I, j equal to 0. For n basis functions, this condition leads to n possible values of w, which are called the eigenvalues. The lowest value of w provides an upper bound for the ground state energy. The second lowest value gives an upper bound for the first excited state, and so on. For each value of w, we can determine ratios of the coefficients to c sub 1, that is c sub 2 over c sub 1, c sub 3 over c sub 1, and so on. In other words, we can only determine n minus 1 independent coefficients. We need one additional condition to determine all n coefficients. That's the normalization condition, which requires that the sum of the squared magnitudes of the coefficients must be equal to 1. To summarize, setting the secular determinant equal to 0 allows us to solve for the allowed eigenvalues, our variational estimates for the lowest energies. For each allowed eigenvalue, we can solve for a corresponding eigenvector, which is the set of expansion coefficients for our chosen basis functions. Now let's walk through a specific example of the linear variational method. Suppose we choose two basis functions. F sub 1 equals x times L minus x, and F sub 2 equals the square of F sub 1. For a particle in a box of length L, note that both basis functions obey the boundary conditions for the problem. They go to 0 at x equals 0 and at x equals L. We set up the trial wave function as phi equals c sub 1 F sub 1 plus c sub 2 F sub 2. To determine the coefficients and the variational energy, we set up the secular determinant with elements hij minus wsij and set it equal to 0. Let's evaluate the integrals that go into our secular determinant. h11 is given by the integral of f sub 1, acted on by the Hamiltonian, multiplied by the complex conjugate of f sub 1, and integrated over the interval from 0 to L. Carrying out this calculation gives the result h bar squared over 2m times L cubed divided by 3. Similarly, S11 is the overlap integral of f sub 1 with itself, which evaluates to L to the 5th over 30. Here are the formulas for the remaining integrals: h12, h21, h22, s12, s21, and s22. Finally, when we expand the determinant, we obtain a quadratic function w, which we then equate to 0 to get two possible values of w, corresponding to two approximate energy eigenvalues. Now let's examine the results of this calculation. The lower value of w, which we denote as w sub 1, is equal to 0.1250018 times h squared over ml squared. We now compare this result with the true ground state energy for a particle in a box, where n equals 1. The exact energy, E sub n, is n squared h squared over 8 ml squared, which for n equals 1 gives exactly 0.125 times h squared over ml squared. Comparing these two values, we see that the agreement is extremely good. The percent error is only 0.0014%. Recall that earlier, when we used just f sub 1 as the trial function, we obtain a percent error of 1.32%. With two basis functions here, we achieve better accuracy. This is the case in general. Accuracy improves as we use more basis functions. Next, we substitute w sub 1 back into the secular equations to determine the eigenvector. After normalization, we obtain the coefficients c sub 1 and c sub 2 as shown here. These are the coefficients of f sub 1 and f sub 2 when the trial function is expressed as a linear combination of the two basis functions. Finally, we compare this approximate wave function with the exact solution, psi, which is equal to the square root of 2 over L times the sine of pi x over L. In this plot, the trial function is shown in blue, and the exact wave function is shown in purple. The trial wave function closely matches the exact solution. Now let's examine the higher energy solution from our variational calculation. The higher value of W, which we denote as W sub 2, is equal to 1.293495 times h squared over ml squared. We compare this result with the true excited states for a particle in a box, specifically for n equals 2 and n equals 3. For n equals 2, the exact energy is E sub 2, which is 0.5 times h squared over ml squared. For n equals 3, the exact energy is E sub 3, which is 1.125 times h squared over ml squared. In general, especially for larger basis sets, the second lowest value of W approximates the first excited state. The third lowest value of W approximates the second excited state, and so on. Here, however, we find that W sub 2 is approximately equal to E sub 3, corresponding to the second excited state. This exception arises because both F sub 1 and F sub 2 have symmetry that is inconsistent with that of the first excited state. As a result, both are orthogonal to the true first excited state wave function, and no linear combination of F sub 1 and F sub 2 can adequately approximate the true first excited state. Let's now take a look at the trial function associated with W sub 2. After normalization, we obtain the coefficients C sub 1 and C sub 2 as shown here. These coefficients define the trial wave function as a linear combination of F sub 1 and F sub 2. We now compare this result with the true excited states for a particle in a box, specifically for n equals 2 and n equals 3. The blue curve on both graphs is the normalized linear combination of F sub 1 and F sub 2. Note that it has two nodes. It is also symmetric with respect to the middle of the box. If we imagine the middle of the box as the origin, the trial function would be considered an even function. The value of the function at locations to the left and right of the center at equal distances is the same in both magnitude and algebraic sign. The purple curve on the left is the true wave function for the first excited state, n equals 2. Note that it has only one node in the middle of the box at x equals L over 2. It is antisymmetric with respect to the middle of the box. The value of the function at locations to the left and right of the center at equal distances is the same in magnitude, but opposite in algebraic sign. If we imagine the middle of the box as the origin, the function would be considered an odd function. The purple curve on the right is the true wave function for the second excited state, n equals 3. Like the trial function, it is symmetric with respect to the middle of the box and also has two nodes. From the plots, we see that the symmetry of the trial wave function is inconsistent with the first excited state, psi sub 2, but consistent with the second excited state, psi sub 3. This confirms our earlier conclusion that the variational solution does not approximate the first excited state in this case, but instead more closely resembles the second excited state. Let's now talk about perturbation theory. Perturbation theory is useful when the Hamiltonian can be separated into two parts, such that the eigenfunctions and eigenvalues of one part are known. We denote this part of the Hamiltonian as h hat with a superscript 0 in parentheses. We read this as h naught. We refer to it as the unperturbed Hamiltonian or the Hamiltonian for the unperturbed system. The second term, typically denoted as h hat prime, is what we call the perturbation. This represents a small disturbance to the system. The key idea is that we already know the solutions to the Schrödinger equation for the unperturbed system. H naught acting on psi naught equals E naught times psi naught. Here, E sub n and psi sub n, each with a superscript 0 in parentheses, are the nth unperturbed, or zeroth order, energy and wave function. Perturbation theory then builds on this zeroth order solution, allowing us to calculate corrections in order to approximate the true energies and wave functions using H prime. Here's an overview of how correction terms are determined in perturbation theory. We begin by writing the Hamiltonian as the sum of the H naught and lambda times H prime. Here, lambda is just a parameter that we will eventually set equal to 1. Doing this allows us to express both the wave function and the energy of the system as a power series in lambda. Specifically, the wave function for quantum state n is expressed as the zeroth order wave function, plus lambda times the first order correction, plus lambda squared times the second order correction, plus lambda cubed times the third order correction, and so on. Similarly, the energy for quantum state n is expressed as the zeroth order energy plus lambda times the first order correction, plus lambda squared times the second order correction, plus lambda cubed times the third order correction, and so on. We assume that the series converge when lambda equals 1. Next, we substitute the power series expansions into the Schrödinger equation. H hat acting on psi sub n equals E sub n times psi sub n. This is what we get for the left-hand side. The Hamiltonian applied to the power series expansion for psi sub n ultimately gives us H naught applied to the zeroth order wave function, plus something times lambda, plus something times lambda squared, plus something times lambda cubed, and so on. For the right-hand side, multiplying the power series expansion for E sub n by the power series expansion for psi sub n ultimately gives us the zeroth order energy times zeroth order wave function, plus lambda times something, plus lambda squared times something, and so on. For each power of lambda, we then equate corresponding coefficients. The equation relating coefficients of lambda to the power m eventually leads us to the formulas for the mth order corrections. For example, this is the coefficient of lambda on the left-hand side, and this is the coefficient of lambda on the right-hand side. Further mathematical manipulations eventually lead us to the formulas for the first-order corrections. Let's take a closer look at the first-order approximation. At this level, we approximate the energy as the sum of the zeroth order energy and the first-order correction. So, E sub n is approximately E sub n naught plus the first-order correction, which we denote as E sub n with superscript 1 in parentheses. The formula for this first-order energy correction for quantum state n turns out to be the expectation value of the H prime operator, evaluated using the unperturbed wave function. Here, in Dirac notation, we see H prime applied on the zero-order wave function for quantum state n multiplied by the complex conjugate of the same function, then integrated over all space. If we imagine organizing all integrals like this into a matrix, then we can refer to this integral as matrix element H prime n n. As for the wave function, the first-order correction for quantum state n, denoted here as psi sub n with superscript 1 in parentheses, turns out to be a linear combination of all the unperturbed wave functions other than that for quantum state n. The coefficient c sub k n for unperturbed wave function k is given by h prime k n divided by the difference between the zeroth order energies, E sub k naught minus E sub n naught. Note that the summation does not include k equal to n. Let's work through a concrete example to see how first-order perturbation theory is applied. Consider a one-dimensional particle in a box. Now suppose that the potential is such that V equals a constant, V naught, in the region from x equals L over 4 to 3L over 4, and is 0 everywhere else in the box. This would be the perturbation if we take the standard particle in a box with V equals 0 everywhere in the box as our unperturbed system. We want to estimate the ground state energy using perturbation theory. So, we write the energy as approximately the zeroth order term plus the first order correction. The zeroth order energy is the familiar ground state energy, h squared over 8mL squared. Next, we compute the first order correction, which is the expectation value of the perturbing potential using the unperturbed ground state wave function. We split the integral into three regions, from 0 to L over 4, from L over 4 to 3L over 4, and from 3L over 4 to L. In the first and third regions, the potential is 0, so those contributions vanish. Only the middle region contributes, where the potential equals V naught. So the correction becomes V naught times the integral of the unperturbed ground state probability density over that central region. This gives us a first-order correction of V naught times 2 plus pi over 2 pi. We add this to the h squared over 8ml squared to get the first-order approximation for the ground state. Let's take a look at the first-order correction to the wave functions for the same example. What would be the coefficient of the third unperturbed state in the first-order correction to the second state? Recall that in the first-order approximation, the wave function psi sub 2 is the sum of the zeroth-order wave function and the first-order correction. The first-order correction is a linear combination of all the unperturbed wave functions, except for psi sub 2 naught. The coefficient for psi sub 1 naught is c sub 1 2. The coefficient of psi sub 3 naught is c sub 3 2, and so on. The question is asking for the coefficient. The formula for coefficient c sub k n is h prime sub k n divided by the difference in unperturbed energies, E sub k naught minus E sub n naught. Here, we just want C sub 3, 2, that is, k equals 3 and n equals 2. E sub k naught is the unperturbed particle in a box energy for psi sub 3 naught, which is 9h squared over 8ml squared. And E sub n naught is the unperturbed energy for psi sub 2 naught, which is 4h squared over 8ml squared. The numerator is the matrix element h prime 3 2, which is the integral over the region from L over 4 to 3L over 4 of the product of the complex conjugate of psi sub 3 naught, V naught, and psi sub 2 naught. When we evaluate this integral, we find it to be equal to 0. Therefore, the coefficient c sub 3 2 is also 0. Let's now turn to degenerate perturbation theory. We begin by considering a set of zeroth-order wave functions, psi sub 1 naught, psi sub 2 naught, and so on. Now suppose the corresponding energies are such that states 2, 3, and 4 have the same zeroth-order energies. We say that they form a degenerate subspace. Now, let's ask an important question. What is the coefficient of psi sub 3 naught in the first-order correction to psi sub 2? Referring to the earlier slide, this coefficient would be given by this formula. But here we immediately run into a problem. Because the states are degenerate, the denominator in this formula is 0 since the second and third states have the same zeroth-order energies. We get division by 0. This tells us that the standard perturbation theory expression breaks down. This formula works only for non-degenerate states. So how do we fix this? The solution is to replace the original degenerate wave functions with a new set of wave functions, which we call the correct zeroth-order wave functions. These new wave functions are constructed so that the perturbation matrix is diagonal within the degenerate subspace. In other words, all off-diagonal matrix elements of H' between these states are 0. This means that H' 2, 3, H' 2, 4, H' 3, 4, and so on are all equal to 0. As a result, if we use the correct zeroth-order wave functions, we say that there will be no mixing between states within the degenerate subspace, and the problematic coefficients become 0 rather than undefined. The remaining question is, how do we actually construct these correct zeroth-order wave functions? That is what we will address next. Let's now see how we construct the correct zeroth-order wave functions in degenerate perturbation theory. Consider a simple example with two degenerate zeroth-order wave functions, psi sub 1 naught and psi sub 2 naught. Our goal is to replace these with two correct zeroth-order wave functions, which we denote as phi sub 1 naught and phi sub 2 naught. Each of these correct wave functions is written as a linear combination of the original degenerate functions. So phi sub 1 is expressed as c sub 1 psi sub 1 naught plus c sub 2 psi sub 2 naught. We get a similar expression for phi sub 2, but with different values for c sub 1 and c sub 2. Our task is to determine the coefficients in these linear combinations. To do that, we solve a matrix equation very similar to what we used earlier for linear variational calculations. A times c equals 0. For n basis functions in the degenerate subspace, the secular matrix A is an n by n matrix, with elements given by H' minus the first-order energy correction times the Kronecker delta. Recall that Kronecker delta, with subscripts I and j, is equal to 1 if I equals j, 0 otherwise. In our example, here, n is 2, and matrix A is this 2 by 2 matrix. The vector c, known as the eigenvector, contains the n unknown coefficients of the linear combination. For the case of two degenerate states, this is the matrix equation. Solving this equation will allow us to determine both the first-order energy corrections and the correct zeroth-order wave functions. One possible solution is the trivial solution, where all coefficients are zero, but this is not physically meaningful, since it corresponds to a wave function that is zero everywhere. Instead, we look for non-trivial solutions, which we obtain using the same procedure we learned in the lesson on the linear variational method. As a result, if we start with n degenerate zeroth-order wave functions, we obtain n possible solutions. First, we find n eigenvalues, which represent the first-order corrections to the energy. Each of these corresponds to one of the corrected zeroth-order wave functions. Importantly, the perturbation lifts the degeneracy. The originally equal energy levels split into distinct values. Next, we obtain n eigenvectors, one for each eigenvalue. Each eigenvector consists of coefficients that define a corrected zeroth-order wave function as a linear combination of the original degenerate states. So each corrected wave function can be written as phi equals c sub 1 psi, a sub 1 naught plus c sub 2 psi sub 2 naught, and so on. Finally, notice that in this corrected basis, the result looks just like the non-degenerate case. The first-order energy correction is simply the expectation value of the perturbation with respect to the correct zeroth-order wave function. Now let's introduce time-dependent perturbation theory. First, recall that if the Hamiltonian is independent of time, then stationary state solutions exist. These solutions are denoted by uppercase psi, which depend on coordinates q and time t, and can be written as a factor that depends only on coordinates, denoted by lowercase psi, times a time-dependent factor, given by e to the minus I et over h bar. Stationary states have well-defined energy E. We solve for lowercase psi by solving the time-independent Schrödinger equation. H hat acting on lowercase psi equals E times lowercase psi. The general solution to the time-dependent Schrödinger equation is then a linear combination of these stationary states. That is, the full wave function can be written as a sum of stationary states, each multiplied by a constant coefficient. Now, consider what happens when the Hamiltonian depends on time. We write the Hamiltonian h hat as h naught, the part that does not depend on time, plus of the part that depends on time, which we treat as a perturbation h prime. Setting h prime equal to 0, we can solve the zeroth-order wave functions and energies. So we can use the stationary states of h naught as our zeroth-order or unperturbed wave functions. Because the zeroth-order wave functions form a complete set, we can expand the general solution to the full time-dependent Schrödinger equation as a linear combination of these states. However, since the perturbation actually depends on time, the coefficients for the linear combination also depend on time. Time-dependent perturbation theory is the method we use to determine how these coefficients evolve in time under the influence of the perturbation. Let's now look at an important application of time-dependent perturbation theory. Suppose the system is initially in a stationary state, psi sub n naught, at time 0. Then, a time-dependent perturbation, h prime, is turned on and acts on the system up to some time t sub 1. After that, for times greater than t sub 1, the perturbation is turned off again. What is the probability of finding the system in another stationary state, psi sub m naught, after the perturbation is turned off? In general, while the perturbation is on, psi will be a linear combination of the zeroth-order wave functions, but the coefficients will be changing with time while the perturbation is on. When the perturbation is turned off at time t sub 1, the coefficients from that time going forward will remain constant. As we have seen in an earlier lesson on the postulates of quantum mechanics, the probability that the system will be in stationary state psi sub m naught is equal to the square magnitude of coefficient of psi sub m naught at time t sub 1. So, time-dependent perturbation theory allows us to calculate how likely it is for a system to transition from one state to another due to a time-dependent disturbance. Now let's look at a physical example. The interaction of light with matter can be treated as a time-dependent perturbation. Imagine a plane polarized electromagnetic wave propagating along the positive z direction. The electric field of this wave oscillates in time and space. If it is oscillating in the xz plane, then we can write it as E equals E sub x, which is equal to E naught times sine of 2 pi nu t minus 2 pi z over lambda. A charged particle in this field would experience a force along the x direction equal to q times E, where q is the charge and E is the electric field strength. From this, we can determine the potential energy. For a system of more than one particle, the potential energy is equal to the sum over all particles of charge times x-coordinate times the electric field. Since the electric field is oscillating, we can treat the potential energy of interaction of the light with the system as a time-dependent perturbation. Suppose the system is initially in a stationary state, psi sub n naught, and a time-dependent perturbation h prime, due to an EM wave, is turned on until some time t sub 1. Using perturbation theory, we can calculate the coefficient b sub m at time t sub 1. The square magnitude of b sub m tells us the likelihood of the system transitioning into stationary state psi sub m naught. Take a look at the integral written here in Dirac bracket notation. The operator between the bra and the ket is the sum of q times x for all charged particles in the system. This is simply the classical expression for the x component of the dipole moment vector, often denoted by the lowercase Greek letter mu. Note that we assumed that the electric field vector oscillates only along the x-axis. We would need to make adjustments if it has non-zero components along the y and z axis. Using mu hat as the operator between the bra and ket account for the general case. Since the functions in the bra and ket are the wave functions of the final and initial states, this integral is called the transition dipole moment integral. Note that the transition dipole moment integral is proportional to b sub m. This means that the larger the transition dipole moment integral, the more likely the system will undergo an optical transition to state psi sub m naught. This idea forms the basis for selection rules. If the transition dipole moment integral is 0, the transition is said to be dipole forbidden, meaning the transition probability is extremely small. Often, the symmetry properties of the wave functions allow us to determine whether the transition dipole moment integral is 0 without carrying out a full mathematical derivation. Let's take a closer look at another factor affecting transition probability, the function shown here as f, which depends on the frequency of the EM wave and the energy difference between the states. This is the complete expression for f. In this expression, nu sub m, n, is equal to the difference between the energy of the final and initial states, divided by Planck's constant. Note that if the final state energy is higher than the initial energy, nu sub m, n, is positive, and we can say that the system absorbed energy from light. The process is called absorption. Otherwise, nu sub m, n, is negative, and we can say that the system lost energy. Interaction with light caused the system to release energy. Light is emitted with frequency equal to the absolute value of nu sub m, n. The transition is called stimulated emission. If we examine the expression for function f here, we see that it becomes significant only under specific conditions. In fact, it is negligible unless the frequency of the light, nu, is close to the absolute value of nu sub m, n. This is essentially the Bohr frequency condition we learned in earlier lessons. Transitions can occur when the frequency of the radiation matches the energy difference between the two states. In reality, however, there is a small but finite probability for transitions even when this condition is not exactly satisfied. This arises from the uncertainty principle. States with finite lifetimes have an uncertainty in energy, leading to a spread in allowed frequencies. Finally, it's important to note a limitation of this treatment. This theory does not account for spontaneous emission of light in the absence of an external electromagnetic field, unless we treat the electromagnetic field as quantized. In other words, we would need to use quantum field theory, which treats light as photons instead of using the classical EM wave treatment, as we have done here.